Today we're going to talk about apparent forces in circular motion. In other words, what do you perceive as you undergo circular motion as opposed to what's actually going on. Let's do a bit of a warm-up. You're in a car moving at constant speed around a circle. At the moment shown, you are headed north. In what direction is the net force on you? And we know that the acceleration for going around a circle, there must be a component which is towards the center of the circle, which, if this is north, this must be west. Imagine you're in that car. Newton's first law says that absent a force, you would continue moving straight. The door of the car provides that force, moving you in a circle. So if you've ever been in the experience of a car going quickly around a turn, in this case a leftward turn, you might have felt thrown against the rightward side of the car, against the door. And you do push against the door, because without the door, you'd keep moving straight ahead. Instead, the door pushes on you towards the center. That gives you the centrifugal acceleration that allows you to move around the circle. The acceleration this way turns your velocity so that you move around the circle. That's not what your brain thinks, though. Your brain interprets signals as if you were an inertial reference frame, quote-unquote, at rest. Your brain basically always thinks that you're at rest. Since the door pushes on you, but you don't seem to move relative to it, your brain concludes there must be a force pushing you outward. In other words, your brain is doing the following mental gymnastics. That's the free body diagram. There's the gravity pulling you down. There's the seat normal pulling you up. And then you're pushed against the door, which you feel. All right, so you feel that the door is pushing out this way. And so your brain concludes there must be some sort of force pushing the other way, because the brain thinks that you're not accelerating. So there must be, since first law, your brain's trying to make first law happen, and so therefore it invents this outward force. There must be some force pushing you against the door, so the door will be pushing back against you. We call that outward directed force a centrifugal force, meaning center fleeing force. The key thing, however, to understand about it is that in a physics sense, it's fictitious. That doesn't mean it's not real so much as it's not Newtonian. It doesn't fit Newton's laws, because it's not happening in an inertial reference frame. So first law doesn't hold in the reference frame you're talking about, so none of the others do. So you can't really do force analysis, even though your brain is desperately trying to. Because it's fictitious, it never appears on free body diagrams. Notice that the centrifugal force never does, and the centripetal force never does. Only forces from physical agents appear on the free body diagram. So this person's going around this amusement park ride with some speed, apparently constant, and they ask, where must the person's apparent weight exceed their true weight? And the key thing here is, where must it be true? Not where can it be true, but where do we know it has to be true? Remember, at the bottom, the net force is upward because the acceleration is upward, and the net force always points in the same direction. The same direction as the acceleration. So at the bottom, our free body diagram is this. Gravity pulling down, and a normal which must be longer pointing up, because the actual acceleration is up. At the top of the arc, the acceleration points downward. There's, of course, the weight, but we don't know. The normal force points in the same direction, so we don't know which of those is bigger. They might be equal. It might be either one of them. So it could be that the normal force exceeds the weight, or it could be the normal force is 0. We don't know. At the bottom, however, the normal force must be more than the weight, so as to produce a net force which points upward. Let's focus back on the top of the ride. This is our free body diagram. We're on old style. I guess the new AP style would be the single dot. Well, I guess actually it would look basically the same, so I'm not going to redraw it. They would just have that be, they would have, I guess this would be the dot. Anyway, so if we take downward as positive, since all our vectors point that way, we find that the net force, which is the normal plus the weight, is equal to m times a, and we know that a is v squared over r. So this is really just saying the net force equals MA. Sorry, it's pretty badly drawn. That the net force, having trouble with my sigmas today, is M times A, because that's A. So we could solve that for the normal force, which remember is the apparent weight of the person. And here we find that the normal force is some number minus the weight, where the number depends on V. The larger V is, the larger Fn has to be. That makes sense. The faster we go around the circle, the harder the chair has to push on us to keep us going in that circle. But it's more interesting if we sort of think about it the other way. Note that there's a speed where Fn would be 0. And there's a speed, if you go any lower than that speed, Fn would have to be negative, which is not possible. The normal force doesn't push you, it doesn't pull you in, it only pushes you out. So the speed at which the normal force is 0 is what's called the critical speed. All right? Critical speed, critical is a term in physics often where we say behavior changes from one type to another. And at that speed, anything slower than that speed, you can no longer execute the circle. That speed, of course, would be just the square root of GR. So, for instance, if the loop is of radius 25 meters, what would the critical speed be? You would just put square root of 9.8 meters per second square times 25 meters, and we would get 15.7 meters per second. Anything slower, and the person would not make it around the loop. Now, in a real amusement park ride, most likely you'd have restraints so that you would fall against the restraints, and they could exert the equivalent of the necessary force to keep you going around, but you would not be able to execute it on your own. All right, let's try some applications. Physics textbook swings back and forth as a pendulum, one of the more useful uses of it. What is the correct free body diagram when the book is at the bottom of the swing and moving to the right, as shown over here? Well, at the bottom of the swing, moving to the right, the acceleration would be towards the center of the circle. So the net force must point upward. So the tension in the string must exceed the gravitational force. We know that we have the weight pulling down, so the tension would have to be more. And these are the only things in contact with the book, so those are the only forces we have. So therefore, it would have to be this one. The coin sits on a turntable as the table steadily rotates around counterclockwise. What force or forces act in the plane of the table? So the coin is doing this as the table does that. They say in the plane of the turntable because we don't care about the normal force or the gravitational force, at least in this particular context. Between the table and the coin, there would be a static frictional force. Why static frictional? It's not sliding against the table, even though it's moving. It's not moving relative to the turntable because it just sits there. So we need to have, let's see, so I guess we can say this is out. And then it kind of gets a little interesting. You're like, well, if the coin is moving this way, won't static friction oppose it? But the turntable is also moving that way. So there is no static frictional force that way, and therefore no static frictional this way. So these are out. But there is static frictional force, so that's out. And we're left with the somewhat uncomfortable answer of this. The static friction here needs to move the coin, has to accelerate the coin towards the center so that it executes the same circle as the patch of the table that it's on. In other words, the table, if you imagine that it's sitting on a dot of paint so we can track it, that dot of paint is being accelerated towards the center because it's moving in a circle, which means that the coin needs to also be accelerated that way, and static friction is the only available force. So it must be static friction that's doing it. A car turns a corner on a banked road. Which of the following diagrams could be the car's free body diagram? Doesn't have to be, but could be one of these. So let's do what we always do. Let's start talking about what forces we have. And the forces that we have of course, there's the weight pulling down, and there's a normal, which is at perpendicular to the surface. So we have to have at least those two, which means that this one is out. Also, let's see now, we need to have gravity pointing directly downward, so this one is out. Then it gets a little, maybe tricky is the wrong word, but we start thinking about it. We could have a frictional force. If we had a frictional force, it would have to point either down the incline or conceivably up the incline. But that would mean that both of these are out because neither of these point in those directions. So by process of elimination, it'd have to be this one. Is this one valid? Sure. If we were to take these and we were to add up the net force, so we take this and we add in gravity, which looks about like that. And then we add in, oops, we add this guy in. Then we get a net force which points more or less the right direction. So that's believable. Here that diagram is drawn a little bit more believably, where they've kind of faded out the actual physical forces and say what's the net force, and if you see as they add up over here, which is what we would need, so it can be the right diagram.